Hello, this is Alex Howe with the Science Meets Fiction Exoplanets review for April of 2022. And this has been another video that's taken a while to make. Part of the reason for that is that I was at the Exoplanets 4 conference at the beginning of the month, and there was a lot of great new science there. I don't have anything specific to say about that, but you can find a lot of what was said on the archive already. Several people were doing live tweets of the conference, and videos of many of the talks should be publicly available in the coming weeks. And after the conference, it's proposal season, so that's taken up a lot of my time. I also don't have any papers to talk about specific newly discovered exoplanets. I think I've mentioned this before, but most newly discovered planets aren't the most interesting things in the field. Certainly many of them are interesting, but there are a lot of them. So it takes something really unusual to make it to the top and be selected for one of these reviews. So I'm going to start with a couple of papers I found about planet populations, because that lets us look at a bunch of planets at once. And the first paper on my list for April was Planets Across Space and Time 3. Which looked at the radius valley in exoplanets as a function of stellar age and metallicity. Now here we can see your classic radius period diagram of planets discovered by Kepler and K2 and TESS and similar transit missions. And you can see the well-known radius valley at just under 2 Earth radii where there are very few planets, which is believed to be due to atmospheric evaporation. This study looked to see if that valley changes for younger and older stars, and more importantly, for metal-rich and metal-poor stars. And of course, in astronomy, metals are anything heavier than helium, and include just about any solids, so more metal-rich stars are expected to have more large planets. And when they looked at stars with different metallicities, they found something interesting. The most metal-rich stars had more mini-Neptunes that are more massive than Earth and have thick hydrogen atmospheres. Going to more metal-poor stars, there are fewer of them, but also the radius valley seems to disappear. For planets that aren't that much more metal-poor than our Sun, we don't really see a radius valley, and we see a lot more super-Earths that are closer to Earth in size. So that's an interesting result, but keep in mind these are statistics of small numbers here. We do not really have enough planets in the sample to see if they really have a different distribution or if it's just a statistical artifact, so we need more follow-up of these transiting planets to be sure. The other interesting paper I saw about populations was about free-floating planets. Free-floating planets, sometimes called rogue planets, are planets that are not attached to any star, and since they don't have any starlight to reflect, you would think they would be pretty much invisible, but that's not quite true. We can detect them by microlensing. As I've mentioned in previous videos, microlensing occurs when a star and planet pass in front of a background star, and the foreground star's gravity bends the light from the background star around it in a way that makes the background star appear brighter. But it doesn't just have to be stars. Free-floating planets can also cause microlensing that is visible from Earth. So this study looked at microlensing events that were weaker than those seen from stars, ordered by the radius of the Einstein ring, which is the circle around an object where the lensing effect is the strongest. And the odd thing about that is this thing called the Einstein desert, where there are very few microlensing events with an Einstein radius between 9 and 26 micro-arcseconds. And this here is the cumulative distribution, so the flat line at the Einstein desert indicates few to no events in that range. Now again, microlensing also relies on small number statistics, but they've done the statistics on them, and the Einstein desert seems to be robust. Now, why is that? Well, it has to do with the mass distribution of free-floating planets. we can make a pretty good estimate of that mass distribution because most of the microlensing events are about at the same distance. They happen in the galactic bulge, where stars are densest, and so they pass in front of each other most often. And that's about 8 kiloparsecs, or 26,000 light-years away. And at that distance, we can calculate that the small lensing events of 4 to 9 microarcseconds are actually caused by super-Earths, free-floating planets only a few times the mass of Earth. Whereas the large lensing events, greater than 30 microarcseconds, are caused by brown dwarfs, significantly more massive than Jupiter. And this has to do with formation. During planet formation, lower mass objects are preferentially thrown out of the system by gravitational interactions with more massive planets. So we would expect smaller free-floating planets to be more common, down to our detection limit. The brown dwarfs are a separate population because they form as part of the stellar population from the primordial nebula, so they don't need to be ejected from systems. So there's a pretty good physical explanation for the Einstein desert there. The other interesting thing they calculated was that there have to be a lot of free-floating planets out there. In fact, they calculated between 130 and 200 Earth masses per solar mass of free-floating planets. And note, that's not planets per star, that's Earth masses per solar mass. Most of these planets are larger than Earth, and most of the stars are smaller than our Sun. But it still means there's significantly more free-floating planets than stars out there. Now, moving on from observing planet populations, let's look at new developments in planet characterization. As it happens, I was an author on one paper to come out last month, a multi-planet system's sole superpuff, exploring allowable physical parameters for the cold superpuff HIP 41378F. And I've put out a couple other papers in recent months, but those were not strictly speaking exoplanet papers. This was an effort led by Michelle Belkovsky and Juliette Becker at Caltech, and we used my Planet Solver planetary structure code in order to compute possible structures for this very strange object. HIP 41378F, also known as K293F, is a superpuff, and that is a planet that is super Earth in mass, only a few times Earth's mass, but extremely low density, in fact down around the density of styrofoam, because it has an extremely fluffy and extended atmosphere. And some hot Jupiters can get down to that density, but hot Jupiters orbit very close into their stars. They absorb a lot of heat from their stars, so it makes sense that their atmospheres would be that fluffy. Superpuffs are harder to explain because they tend to occur at larger distances. So we used the Planet Solver code to calculate possible internal structures of core mass and the depth of the hydrogen envelope. And it's pretty crazy. This planet is only 12 times Earth's mass, so less than Neptune, but 9.2 times Earth's radius, which is about the same as Saturn. So it's one of the most extreme superpuffs around. And in fact, the only plausible solutions we could find were that it is at least 75% hydrogen by mass, and for Neptune mass planets we expect maybe 10% hydrogen by mass. This one comes out to at least 75%, and depending on the entropy of the atmosphere, which is sort of a proxy for temperature, 100% hydrogen composition would still fit, even though that's very unlikely. Now, we do know this composition is probably pretty close to primordial. This planet is far enough out that it will not have experienced any evaporation of its atmosphere, we think. At least not photoevaporation. The inner planets B and C would have lost a lot of their envelopes, but the outer planets would not have. But even with no evaporation, this is a very high hydrogen fraction. Now, I should note that other recent studies have suggested that the large radii of superpuffs could be an artifact of absorption but that's not settled yet. Dusty outflows of an escaping atmosphere, rather than simply a very fluffy atmosphere, but that is still very much an open question. Next, we have a spectroscopic study of another very unusual planet, 55 Cancri e. 55 Cancri e is an ultra-short period planet, which means it has an orbital period of less than 1 day, so extremely close to its star and extremely hot. And that close to its star, we expect it to not have an atmosphere. The entire atmosphere should have evaporated. And for most ultra-short period planets, we've found that is the case. The observed radius and mass suggest that they do not have atmospheres, except for 55 Cancri e. 55 Cancri e's radius is too large to make sense with just a bare rock. So this study took a spectrum and looked for signatures of various elements that we would expect from a rock vapor atmosphere. Because this planet is so hot that we expect its surface is molten, and you could have outgassing from the lava on the surface forming a thin atmosphere. However, as it turns out, they didn't actually find anything. They found upper limits, some of which are high enough to be interesting, but they could not positively detect any of these elements. And that could be due to some kind of high temperature hazes or something. But for now, 55 Cancri e remains a mystery. Moving on from characterization, there were some interesting papers about the theory of atmospheres. This one looked at interstellar comets, like the famous interstellar object Oumuamua that was discovered a couple years ago, and another more recent one, Borisov. Objects that we've seen flying through our solar system on trajectories that mean they're not gravitationally bound to the sun. And they looked at what circumstances in planet formation would cause something like this. And it mainly has to do with formation of large Jupiter-like planets and their distance from the star. For large planets forming close to the star, they will tend to sweep up comets with their gravity when they pass close to the star. For the actual Jupiter, some comets are accreted, like famously Shoemaker-Levy 9, which collided with Jupiter in 1994, and some comets will be thrown out of the solar system. And if you have planets forming in very distant orbits, where they would plow through the exo-Kuiper belt or Oort cloud where the comets form, they would be more likely to simply eject comets away from the star and into interstellar space. And this makes a relatively sharp line through the mass semi-major axis diagram, where hot Jupiters and warm super-Earths will accrete comets, have comets collide with them, but many cold Jupiters will eject them from the system. Next, this was a really interesting one to me. The upper edge of the Neptune desert is stable against photoevaporation. So the Neptune desert is this region of the parameter space of planets, in this case mass and orbital period, where we don't observe very many planets. Now in this case, because it's in terms of mass, it's somewhat less surprising than if it was by radius. The Neptune desert in radius is believed to be due to photoevaporation, where a Neptune-sized planet very close to its star would have its atmosphere very quickly stripped away, becoming a smaller super-Earth, whereas gas giant planets could retain their atmospheres. But they looked at it, and at least looking at it in terms of mass, this seems not to be the case. Specifically in that many planets at the edge of the Neptune desert could very easily retain their atmospheres, and planets that somehow fell in the middle of it could still retain a large fraction of their atmospheres. And yet we don't see any in that region. And that would suggest that the Neptune desert is actually some kind of signature of formation and migration of planets, where Neptune-sized planets cannot successfully migrate in the same way that hot Jupiters can. They either don't get in that far or eventually collide with the star. So that's definitely something to keep an eye on, as more work is done on these objects. Another paper about mass loss, the impact of time-dependent stellar activity on exoplanet atmospheres. This is asking, we know that close-in planets do undergo at least some photoevaporation and lose part of their atmospheres to ultraviolet light from their stars. But for planets specifically orbiting red dwarfs, it's a little different because many red dwarfs produce intense flares, hundreds or thousands of times more powerful than our sun's solar flares. And these flares deliver a lot more ultraviolet and X-ray light all at once, which could affect the rate of evaporation of their atmospheres. And you can see in the spectrum that stellar flares produce a lot more light at certain specific wavelengths. And they calculated that when exposed to a flare, a planetary atmosphere could undergo physical and chemical changes, which would lead it to absorb a lot more energy from the star. And when it absorbs more energy, the atmosphere will escape faster. So that suggests, and I think this has come up before in this series, that flares are an important component for calculating photoevaporation rates. On a similar note, we have the relative importance of AGN winds for the evolution of exoplanet atmospheres. AGN winds are these massive galactic-scale winds produced by supermassive black holes. If a supermassive black hole is eating a lot of gas or even stars, it will put out a lot of energy as a byproduct. This energy takes the form of galactic winds, kind of like the solar wind, and for planets close to the galactic center, those winds could be more powerful than its own star's solar winds, and affect the planet directly. Of course, normal stellar heating, just heating from sunlight, is a much stronger factor in atmospheric evaporation than the solar wind is, so this is really a secondary effect. Next, we have a different mass loss process, atmosphere loss in oblique super-Earth impacts. And this paper is based on the idea that during planet formation, planets sometimes collide. That's how our own moon formed. But for super-Earths, or rather mini-Neptunes, that have these large extended atmospheres, you could have these grazing collisions where the solid parts of the planets don't touch, but one plows through the atmosphere of the other, and just that close encounter could blow away a lot of the atmosphere. So the team did a bunch of simulations of various types of collisions along these lines, and they found they fell into 3 broad categories. If planets hit head-on, they'll merge together. If they hit off-center but still hit solid surface on solid surface, you could form a moon like our own. And if they just graze through each other's atmospheres, you have a hit-and-run collision where they keep going and will blow away a lot of the atmosphere. However, they determined that stripping away the entire atmosphere is unlikely, so this is not a mechanism for simply turning mini-Neptunes into super-Earths. Next up, there were a surprising number of interesting papers in April about planet formation and geology. To start with, there were 2 papers back-to-back about formation of Mercury-like planets. And these are kind of borderline as exoplanet papers since they really do focus on Mercury, but they look at the entire population of Mercury-like planets. So I think they still count. The first one is Nucleation and Growth of Iron Pebbles explains the formation of iron-rich planets akin to Mercury. And both of these papers are based on the fact that Mercury is very iron-rich. It's about twice as iron-rich as the other rocky planets in our solar system. And it has an iron core that equals about 70% of its mass. And there are other exoplanets that are observed with similarly high densities. Now, traditionally, Mercury's high iron content was theorized to be due to a giant impact. Not like the moon-forming collision, but something that stripped away most of the mantle, leaving just the core. But this new model suggests maybe that's not the case. Instead, they say, chemical processes in the protoplanetary disk will cause iron and rock pebbles to form separately, and coalesce into planetesimals separately. And so there would be this natural segregation between rock and iron, which could produce both rocky planets like Earth and iron-rich planets like Mercury. So a giant impact is not necessarily needed. However, just a couple days later, this paper came out, forming iron-rich planets with giant impacts. And this team did a statistical model of giant impacts and the composition of the planetary fragments that would be produced by them, and compared it with Mercury and some of these other apparent iron-rich planets that have been discovered. And they found that the giant impact model does plausibly match the iron-rich planets we see. So the jury's still out on what is actually forming these planets. Then there were several papers about plate tectonics. And this may seem a little unusual to talk about in the context of exoplanets, because we can't very well see earthquakes and volcanoes from interstellar distances. But we can model them. And we can model how they might impact habitability. And this is what Sarah McIntyre did in Tidally-driven tectonic activity as a parameter in exoplanet habitability. So the theory goes that Earth's plate tectonics, with multiple continental plates moving around Earth's surface, help to maintain Earth's habitability, because they sort of regulate the CO2 levels in the atmosphere. It also appears that Earth's plate tectonics are dependent on an ocean to change the composition and viscosity of rock to make moving the continental plates smoother and more reliable, for lack of a better term. In contrast, Venus appears to have what is called stagnant lid tectonics, where the plates don't move, or there aren't really plates at all, just a solid surface. There can still be volcanoes from volcanic hotspots similar to the Hawaiian Islands on Earth or Olympus Mons on Mars, but there's nothing like the Pacific Ring of Fire, where plates are grinding against each other. And with this weaker volcanism, there are concerns that it would also weaken their habitability. Now, personally, I think these concerns are very speculative, but it is something that is being looked at. But there's an additional wrinkle that tidally locked planets will be undergoing different tectonic forces, especially in a compact super-Earth system like, say, TRAPPIST-1, where the planets pass relatively close together. These planets could be kept hot by strong tidal forces like those operating on Jupiter's moons Io and Europa. And these are very different tectonic processes to compare with Earth in terms of habitability. So in this study, Sarah McIntyre calculated that if there is enough tidal stress, you could get a mobile lid of tectonic plates like you have on Earth. The danger is that if there's too much tidal stress, the planet gets too hot and boils off the water. Luckily, some important M-dwarf planets like Proxima Centauri b and GJ 1061d fall right in the sweet spot where you get mobile lid tectonics. But I want to reiterate, it is very speculative that you really need mobile lid tectonics to maintain a biosphere. Hotspot volcanism, erosion processes, recycling through the oceans, there are a lot of other things that can affect the carbon cycle, and it's perfectly reasonable to think a planet could reach a habitable equilibrium without Earth-like tectonics. Even so, there was another paper on this topic. Mantle degassing lifetimes through galactic time and the maximum age stagnant lid rocky exoplanets can support temperate climates. And this is basically based on the same premise. No longer tidally locked planets subject to strong tidal forces, but something more like Venus, where the crust just seems to freeze out at a younger age than Earth. And there can be quite a range in tectonic activity, because tectonic activity is partially driven by radioactive heating from uranium, thorium, and potassium incorporated into the planet during its formation. About half of Earth's internal heat is thought to come from radioactivity. But this radioactivity is very unevenly distributed across galactic time and space, because especially for uranium and thorium, it's dependent on neutron star collisions, which are rare and occur in specific stellar environments. So this team essentially did simulations calculating how long it would take for planets with stagnant lid tectonics to freeze out and lose their volcanism. And they determined that the timescale is much shorter than Earth. Only a couple billion years, in fact. Now this is interesting because Venus appears to have had fairly recent volcanic activity by cosmic standards. And I'm not sure how well that meshes with these calculations that its mantle should have stopped degassing and more or less stabilized after just a couple billion years. But it's something that's worth a further look, I think. On a similar note, there was a more speculative paper having to do with volcanism, large-scale volcanism and the heat death of terrestrial worlds. And by heat death, they don't mean the heat death of the universe, but the runaway greenhouse effect on Venus, which is generally presumed to be a common feature of planets in orbits similar to Venus. This is based on the idea that maybe Venus wasn't an uninhabitable greenhouse planet from an early age. Even though it's quite a bit closer to the sun than Earth and gets twice as much sunlight, Venus's clouds today are so reflective that its equilibrium temperature is cooler than Earth's. And for the same reason, if you look at Venus's cloud tops, where the atmospheric pressure is the same as Earth, the temperature is also about the same as Earth. So if it didn't have that super thick carbon dioxide atmosphere, it could still support an Earth-like climate today. I also discussed this in my video on terraforming Venus. So some people speculate that Venus may have been inhabitable and may have even had life as recently as 500 million years ago, and that the runaway greenhouse was a relatively recent development. This theory says that the runaway greenhouse may have been triggered by large igneous provinces. These are very large volcanic eruptions caused by mantle hotspots that can last for millions of years and are much larger than the Hawaiian Islands, covering millions of square kilometers with lava. Famously, the Siberian traps on Earth are a large igneous province that is believed to have caused the largest mass extinction in Earth's history, the Great Dying, or the End Permian extinction, in which something like 80% of all species went extinct. This study looked at what would happen if multiple large igneous provinces happened at the same time, and they conclude that statistically it is very plausible that Venus could have had 2 or even 3 large igneous provinces at once, which may have been enough to trigger the runaway greenhouse on an otherwise habitable planet. Now, of course, the million-dollar question, or maybe even the trillion-dollar question, is, could something like that happen on Earth? And we don't know, but no. Let me explain that. I actually had the opportunity to ask Michael Way this directly last month, and he said it's something that they're still investigating, and they don't really have results yet. But also, we should keep in mind that it would take an estimated 45 degrees Celsius of warming to put Earth at serious risk of a runaway greenhouse effect, not 3 degrees or 6 degrees or even 12 degrees that you see in climate models. So could it happen on Earth in the next billion years? Maybe. But not something we need to worry about today. There's enough stuff to worry about as it is. Here's an interesting paper on the SETI front. Disruption of a planetary nitrogen cycle as evidence of extraterrestrial agriculture. And this is simply asking if aliens are farming, and that farming bears some reasonable degree of resemblance to farming on Earth, could we detect it? And the answer is maybe yes. Farming on Earth produces non-equilibrium chemistry, like elevated ammonia and nitrous oxide levels. And ammonia and nitrous oxide could leave detectable signatures in a planet's transit spectrum. Signatures that are potentially detectable with something like the James Webb Space Telescope, especially this one feature at about 8 microns. If we can see atmospheres on Earth-sized planets at all, which may have to wait for the next generation telescope as it is, it may well be possible to detect agriculture happening on those worlds. And finally, a plan for a future space mission, which is a long way from being realized, but is definitely possible. Resolved imaging of planets with the solar gravitational lens. And this comes back to the microlensing idea, and I believe I've also mentioned this in a previous video. The sun acts as a gravitational lens, bending light from background stars and planets behind it to form an image in front of it. If, by in front of it, you mean 650 astronomical units in the other direction. That is 20 times the distance to Neptune and about 4 times the distance we've sent any spacecraft thus far. But if you could put a spacecraft out there at just the right location, you would see the sun naturally acts as a giant telescope, and if you block out the actual sunlight, you will find that it produces an image of an exoplanet. Now, this image is actually hundreds of meters wide, so you can't just build a kilometer-sized telescope out there to take a single picture. But a 1-meter telescope moving back and forth across the image could take a pretty good quality picture of an exoplanet directly. And the authors of this paper looked at the requirements to do that, and long story short, it is doable. We would need to have a good candidate planet to image because the telescope has to be at a specific location for a given target, and the technology to put it out at 650 AU isn't quite there yet, but it's definitely doable this century, and I for one think we should give it a try.